Good morning, everybody. My name's John Walter, and I'm the Business Development Manager for TLV Corporation here in Charlotte, North Carolina. I'm going to be presenting this session today with Mr. Richard Newbigin, who's the Northeast Regional Manager for TLV Corporation. We're going to be supported by a number of other TLV members behind the scenes, and I'd like to just introduce them today. So if you could turn your cameras on, please. So first of all, we've got Mr. Jim Risko. He's the president.
Hello, everyone.
Norm White, who's our executive vice president.
Good morning, everybody.
Drew Moore, our consulting and engineering services manager.
Hello.
And Justin McFarland, our engineering manager.
Hello, good morning.
So the presentation we're going to give this morning is based on our experience throughout sites all over the world, but we don't really know your particular site, so we have to give you this disclaimer. Now, so that the rest of this presentation runs smoothly, I'm going to ask if we can all turn our cameras off now, please. So here we've got a steam distribution system, and the focus of today's session is going to be on how the plant can optimize these areas. And that's typically going to be safety, production, reliability, and environment. Now, while the plant is focused on these areas, TLV is focused on the steam system. And we're looking at how the steam is distributed through the system, how it's used in equipment, and how that condensate can be returned. And we have 4 key objectives for that. The first one is to ensure that we're supplying dry saturated steam to the equipment and to tracing systems. We're going to be looking at how we can eliminate steam leaks throughout that system, and also how we can drain condensate as soon as it's formed. And that's important so that it doesn't back up and cause any problems. And then finally, how we can return that condensate back to the steam boiler. Now, these 4 things we approach with a 3 phases of activity. The first one is condensate discharge location management. The second one is improving individual items of steam using equipment, such as turbines, reboilers, or air heaters. And then the third phase looks at everything in the steam system and sees how they interact to optimize the entire system. And that typically involves a steam balance, tracking water consumption, and sometimes looking at the strategy for electrical generation. Now, the 3 phases I've got here are explained in a little bit more detail in one of the articles in the control panel that's also available from this location. Now, today's webinar is going to be focused really on that first stage, CDL management. So let's start by exploring what is a CDL, or condensate discharge location. Here is a steam line, and as the steam travels through here around the plant, it's going to lose heat energy to the atmosphere, even though the pipe is insulated. That means some of the steam is going to condense, and it'll fall by gravity and be collected along the bottom of the pipe. At this point, we need to have something to remove that condensate, and there should be a strategically located condensate collection pocket like this one, so that the condensate can flow in. It'll then be discharged through a steam trap, and ideally sent to a return line back to the boiler system, although it could just be discharged to the sewer system. So for us, a CDL is what's inside this red box. It consists of the steam trap, the isolation valves, blowdown valves, and although I'm not showing it here, also bypass valves and possibly strainer blowdowns. Now, these condensate discharge locations are everywhere, along the steam distribution lines and also around equipment. So here I have an example of a reboiler, but it could equally be anything in your plant, Could be a hot water heater, an air heater, or even a tank coil. And the steam is supplied in here. And then before and after the control valves, we again have condensate discharge locations. And that's particularly important here to remove the condensate before a control valve when that valve is closed to prevent condensate from building up. The steam will get used in the equipment, give up its heat, and then condense. So here on the outlet, we've got another condensate discharge location, this time with a bypass valve and a much bigger steam trap. So the purposes of a condensate discharge location are really to drain condensate. And if that location fails closed, then condensate will back up, and it could cause problems like water hammer, piping erosion, or even production loss. The other function of the CDL is to keep steam in the system. And if it fails open, then steam will be lost, and that's going to waste energy. It's also going to waste water and could present a safety problem. There's a third function of a CDL that's sometimes not talked about, and that's really to vent air. If that doesn't work, then air gets trapped in the system, and that can result in things like slow startups, low temperatures, or if an operator now manually tries to vent that air and allows steam to escape, it can result in steam loss. So our condensate drainage location management program needs to do three key things. It needs to make sure that these CDLs are properly installed, and that means that they're in the right places and properly designed. We need to confirm that the traps are draining condensate and that there is no steam being lost from anywhere in that CDL, either the steam trap, the blowdown valves, or through the isolation valves. And that's a lot more than the traditional way of perhaps doing it with just a trap survey, getting a survey report, and then hoping that the plant makes some improvements. Now, the program we're going to talk about today is actually based on some quality assurance principles. The first one is visualization. It's making things visible so that people can understand and see what's happening, that we can track actions, and we can very clearly see what the benefits are going to be. It's based on protocols, which are standards and procedures that ensure the right action is taken automatically, so the system is self-sustaining. And then finally, on improving each year, every year, and not having any gap years. Now, these quality assurance principles are sometimes known by these names: Miyaruka, Shikumi, and Kaizen. And I'd encourage you to look these terms up on the internet and see if there are some things in them that you could apply to your program. Now, there are some other key points that we're going to be covering during today's presentation. We're going to be talking a lot about maintaining a management program of CDLs, not just doing a trap survey, about how to plan, justify, and budget the program, and to do that before the program starts. We'll talk about the importance of taking maintenance action, because really that's where the benefits are made, not by doing a trap survey. We'll talk about how to keep the program running and improving, and we hope you're going to get some good ideas for best practices you can implement in your own programs.
So what does optimizing the steam system mean? As John showed earlier, there are 3 steps or phases to implementing this program. For most sites, you're going to have about 75 to 90% of your drain locations on your steam supply system. So that makes it a target-rich area to go after in terms of CDL management. John, I don't have control. So when enough CDLs, so how do some customers handle this? When enough CDLs are operating out of spec, plants will often try to alleviate the symptoms by conducting a survey or an audit. Often symptoms such as safety or environmental incidents, or just a visible increase in vent steam or reduction in condensate return will spur them to action. because it's not a planned event, oftentimes sites struggle for budget. So therefore, they're forced to rationalize or try to get the biggest bang for their buck and award the survey to the lowest cost provider. But again, as a relatively unplanned event, once the survey is completed and the data is collected, the failed drain locations are identified. Because there's not enough budget, sites will struggle and they don't replace all of those failed CDLs. And so that means that oftentimes they don't achieve all of the results that they were hoping for. Maybe they don't save as much money. And when the system is completed, frequently the lack of savings or the initial symptoms being resolved result in the site returning to their previous paradigm and of non-maintenance of the asset. So next, after years of repeating that, where does that leave the plant staffs? Well, typically we find that they're aggravated at wasting maintenance budgets by frequently replacing steam traps. We find that they're irritated by unplanned maintenance expenditures to fix steam equipment like reboilers or turbines, any type of steam using equipment. Oftentimes they're fed up with having to work around process problems like bottlenecks or product quality issues or freeze-ups. And they're concerned that they're paying for surveys on an ongoing basis, and there's actually little to no discernible reduction in the actual system maintenance costs for the asset. So non-care of those critical steam assets often results in additional future barriers to efficient and safe operation. Things like water hammer, freezing and slip hazards, flare-outs, increased greenhouse gas emissions, bleeder and bypass valves being open, vent steam increases, reduction in condensate recovery, high inventory costs to maintain spares, resources being diverted and labor being reduced that can sometimes lead to intermittent implementation of the program or gap years, and sometimes even just a year-on-year increase in program costs. And from a production side, anything from unplanned shutdowns to the inability to pull vacuum, issues with sulfur tail gas units, and sometimes excess load on your process waste system from dumping condensate. So next, if sites want to see real reductions, what do we have to do? Well, we have to break that cycle. We have to stop doing things the way we did them. First thing we have to recognize is that steam is an asset. And in order to manage and optimize that asset, it requires a proven step-by-step solutions-based approach to achieve those long-term results. So, what are some of the things that we've observed of common past behaviors that we have to change in order to break that cycle? Well, one of the first is if you're having surveys done, we want to stop soliciting the lowest per trap survey cost. We want to stop accepting inaccurate judgments of the CDL locations. We want to stop focusing on just the percentage of failures, particularly fail open traps. We want to stop just testing the steam trap itself. We want to stop allowing the surveyors on the site to test without adequate operations support in the field. And we want to stop missing opportunities by not replacing all of the failed CDLs. So those are the things we want to try to stop doing. What are some of the new behaviors that we can adopt to drive change for better asset management? Well, those are going to include things like getting a full overview of the cost-benefit ratio for the project before it starts, understanding the total costs. Stop doing reactive surveys. So stop reacting to events and chasing them and get out in front by implementing some type of program. Focus on practicing zero reset maintenance, changing all of the failed CDLs that we find to drive your failure states down to 5% or below. provide operations support for the survey to improve the data collection. Using a total cost of ownership model to evaluate steam trap replacements and repairs. And lastly, we want to focus again the inspection on the entire CDL, not just the steam trap. So the first behavior that we want to try to change is how we purchase our inspection services. So survey companies, historically, if you have someone come in, you get a per trap price. And the question is that the best value for your site? Maybe not. Let's look at why that might not be the best value. So do you want additional data to improve your maintenance planning? Things like trap maps, takeout dimensions of the existing traps, any missing components? Do you want better diagnosis of cold traps? Not just, hey, the trap is cold or everything is listed as blocked, but which traps are not in service, which traps are maybe piped incorrectly that's causing them to be cold, which traps may be undersized. And do you want the entire CDL evaluated? Do you want to know if your isolation valves are leaking? Are there check valves installed? Are the bypasses open? Well, per trap pricing typically incentivizes speed, but that can likely cause a reduction in actually the accuracy and the amount of data that's collected that could be valuable for you down the road. So using a daily rate allowance for accurate and thorough data collection, you can put some performance markers in there in terms of an estimated number of traps per day, but I would encourage you to look at this, like most services, on a daily rate basis. So there are some things that need to be considered before the survey starts, and one of the most important things are, what is inaccurate data costing us? So oftentimes people don't think that there's a big difference based on the accuracy, but let's look at some of the conditions that might occur and what those might be costing you. So a good trap that's judged to be failed would result in obviously an unnecessary replacement. So that could be conservatively estimated at about $350 in time and materials. A leaking trap that's judged to be good presents a lost opportunity to recover that energy. So based on the lower energy costs we're experiencing today in parts of the world, we've estimated that at conservatively about $876 for a steam leak. And a cold trap that's judged as good or not in service presents unidentified risk factors. Now, we've done some evaluation at refinery and chemical plants, and we've estimated that typically to be around $400, but for general plant use, we'll cut that in half for our example and make it $400. So what does all of that amount to on a typical survey? Well, the average inaccurate diagnosis is roughly about just over $500. If we assume a very small deviation, only if you get something that's 97% accurate, only a 3% deviation, that doesn't seem like much, but over 1,000 trap population, that could result in over $16,000 of lost opportunity. That might actually be the same or more than you paid for the entire survey. So it comes out to be roughly about $16 for every trap in the population. So you really want to evaluate what is the survey's real cost to the plant and how much does the accuracy impact that real cost. So what should customers be asking to evaluate the diagnostic accuracy of what they're receiving? So some good questions you might want to ask are, who's making the primary condition judgment? Is it the surveyor, which is going to be typically a subjective judgment, or is it the technology that they're using or the software that's going to produce an objective judgment? Are the surveyors trained and certified to test all types of steam traps? If they are, how often do they receive that training and certification? How much field experience, on-the-job experience do they have? And is the condition judgment, especially if it's objective, is it validated? Is it independently validated? Who's doing that validation? What documentation do they have relative to that? And what reference standards are they using? So at TLV, we've developed a solution to address a lot of these issues. centered around using the TrapMan unit, which some of you may have some experience with. We have statements from independent sources indicating that it's certified accurate and suitable for testing steam traps. We have that regularly tested by third parties, most recently by Hartford Steam Boiler in 2017. And we carry an inspection certificate that confirms that validation by the independent third party. So next, we're going to talk about that paradigm shift away from looking at reducing overall failure rate of fail open traps. So you can see in this graph, this particular client has done over a 5-year program. They've really focused on reducing their failure rate based on their cold or their hot failures and trying to drive down energy loss. So you can see from year 1 to year 5, that red number of the fail open traps is going down. Next. However, during that time, the number of good drain locations actually hasn't changed very much. It's fluctuated between 40 to 60%. So we still have a large number of cold traps or not in service traps because those have not been the primary focus of replacement. So I'm going to encourage you to think about this differently and look at driving up the number of good drain locations. The more drain locations in your plant that are installed, that are working properly, the less issues we're going to have and the better your steam asset is going to perform. So that shift in paradigm away from just focusing on failures to driving up the number of good traps, clearly if the number of good drain locations is going up, the number of failures are going down, but we're also including trying to reinitialize not in service traps if they were supposed to be in service, and clearly defining and eliminating any cold losses. Next. So we talked about testing the entire CDL, not just the trap. Why do we want to do that? Well, we might want to identify the upstream isolation valves, or if there are any. We want to note if the valves around the trap are open or closed. We want to look at and detail any CDL problems we might find. So for instance, is the trap installed incorrectly? Is it above the drain location? Are we missing a check valve on the discharge side? We want to look at bypass valves that might be open and estimate the steam loss. As you'll see later in the presentation, losses from bypass valves can far exceed the loss from a steam trap. And we also want to record locations in the database where there might not be a steam trap, but there should be. Hopefully there aren't many locations like that. But again, you want to note that those are condensate drainage locations that are not being trapped. And the last thing we're going to talk about is Z.R.M, or zero reset maintenance. This is the goal to eliminate all failures and restore the maximum performance to the steam system. So typically it's going to look like this on a year-by-year basis. So the survey gets done, the traps are replaced and retested to ensure proper operation, and we return the system to full operational status. Now, doing that requires upfront planning and budgeting so that we're not reacting reactively to those failures, and we want to focus on minimizing the cost of the Z.R.M by lowering the installation costs and collecting as much data up front that makes it easier to plan that process.
So before we start planning everything, we've really got to answer one important question. Is it really worth it? There are obviously lots of benefits and there's going to be some investments. So for the next few minutes, I'd like to take you through each one of these topics and give you some idea of how much that might be worth. So let's start by looking at the leak from a steam trap. Now that will depend on the size of the trap, its operating type, and basically what model it is. It'll depend on how much it's failed and what pressure it's operating at. Now we've got a huge amount of data that classifies all of this. So I'm just going to simplify that and give you 3 approximate values to start working with. So at the smaller end, steam traps may be leaking maybe just 10 pounds an hour. And if that operates for 760 hours a year, which is the whole year, it might be worth about $450 a year of energy loss. Now, somewhere in the middle, about 20 pounds an hour is a good number to work with. And then up at the larger number, perhaps up to 50 pounds per hour. But again, these are just ballpark numbers to give you some idea. Now, there also are going to be bypass valves and blowdown valves. And occasionally those get opened to alleviate problems. And as Richard said, that can account for a lot bigger loss. So I'm going to take a 3/4 inch valve and just crack it open 2% and look at what happens with 150 PSI steam going to atmosphere. We can take that data, plug it into a calculator. TLV have a great one. It's called the TLV Toolbox. You can download it from the app stores. And we'll very quickly see that we can get a steam flow rate through a valve with those conditions of about 167 pounds per hour. So that's a lot bigger than the 50 pounds per hour for a blowing trap. And that's worth about $7,300 a year. Now, it might be a little bit smaller than that because condensate is flowing through the valve at the same time as the steam, but it could also be more if, for example, we were using a 1-inch valve or we were cracked 3% open. Now, there's another hidden cost, and that's of cold traps or cold locations. And there's a great article, it's in the control panel to your right and available at this location, that talks about how to quantify and financially determine the risk associated with a cold trap. And the methodology involves looking at the plant history and finding incidents that could be attributed to accumulated condensate. So that might be water hammer damage, lost production, or even a safety incident. And the data we need to collect is how frequently that happens, what the financial value of that incident was, and the total number of steam traps. And then we can do some maths and identify a dollar amount, which is a risk per year per cold trap. Now, we've done a lot of work in the refining and petrochemical industry, and we've come up with a number of about $800 per cold trap. And that is very conservative. So today, Richard and I are using half that value of $400 a trap for just general industry. Now, there's another way of calculating the financial impact of cold traps, and that's explained in another article by Dr. Brian Kane. And again, that's available for download in the control panel. There are also some other benefits that are maybe a little harder to quantify. For example, if we have a program that's improving year on year, 5 years from now, that plant should be experiencing less failures. That means there's less products to purchase, and we can free up labor to work on more important things. There's also reduction in safety incidents. We can reduce CO2 emissions because if steam's not leaking, we don't need to burn fuel to generate it, so we're not generating carbon dioxide gases. We can conserve water, and that might be particularly important for sites that are challenged with water treatment facilities. And finally, there may be an impact in production. So that's it for the benefits side. Let's have a look at some of the costs. And I'm going to take a sample plant with 1,000 locations, and I'm going to assume that 300 of them have failed. And that's possibly what we might see with a plant that hasn't been doing a proactive program for maybe 2 or 3 years. So the first cost is to go out and survey all the CDLs. Then we are going to find failures. So we're going to have to purchase some product and some piping to put that right. And then there'll be a labor cost to do the installation. And there'll probably be some other admin costs in there that I'm going to ignore for today, just to keep things simple. Now, the important thing to note here is the cost of the survey is probably only a small part of the total cost of running the program, which in this example is coming out to be about $125,000. We want to stress that the plant needs to budget this full amount before the program starts. And if that amount of money is not available, then it might make sense to put the plant into different sections, survey one section, and do the replacements before moving on to the next. And that way benefits are actually being achieved rather than spending a lot of money on doing a survey and then not so much or indeed no money to do the replacements. So we need to budget for all of these items. So let's put the costs and the benefits together and see what that looks like. So here's the plant, 1,000 locations. And if we can eliminate these cold failures using the $400 per location, we'd have a risk mitigation of $60,000 a year. If we were using that for the refining and petrochemical industry, we could easily double that. By eliminating steam leaks, we'd probably save about $131,000 just in that first year. Now I'm going to take the number we had from the previous slide and say there's the investment cost. We're going to handily ignore the other benefits and costs, but you can quickly see here that we've got a simple payback of about 8 months. And these savings that we generated in the first year would actually carry over potentially into the second year if nothing was done to address them. So some plants will actually look at this on a 5-year internal rate of return basis. And there's a great article that explains how to do this in the control panel. You can download it, also available from this location. And the author there explains how to do a 5-year IRR and shows an example where it comes out to be about 112.5%, which is a very big number. So the question we started with was, is it worth it? And the real important question now is it worth it for you? Well, that's going to depend on the state of your condensate discharge locations and what else and what other challenges you're faced with. So a good starting point is to take a representative sample of CDLs and inspect them and see how they are performing. At the same time, walk through the plant and assess what other challenges are there, as well as how a program could be effectively implemented. So we take that information, now we can extrapolate it over the entire plant. We can estimate what the return on investment is going to be, and the plant can also now start to budget for the whole program. And we can use the background information to start planning a program. And that typically falls into a couple of significant blocks. First one is just general planning and survey planning. And this is where the plant would typically go out and do a survey. We're going to caution against that and suggest it's probably better to plan the maintenance response and actually start to prepare for it and then do the survey. And that way, as soon as the survey results come in, the plant can take action and start making savings. If it's round the other way, the survey may get done, the report comes in, and the plant's not ready to make improvements. And then, of course, everybody gets busy, things get put to one side because of other priorities, and before we know it, the survey is out of date. Now, these are the basic planning blocks. We also want to plan for how we're going to manage the program. And I'll talk a little bit more about that later on. So these core building blocks can be shortened up into a milestone plan. And within each milestone, we can have even more detailed actions that help ensure plants are going to be very successful implementing this program.
So in this section, we're going to review the necessary steps to implement and maintain an ongoing CDL management program with a focus on long-term success and long-term cost reduction. So before starting the program, we want to make sure that, as John indicated, we do a demo. We want to test a certain number of traps, and we want to do a steam system walkthrough to look at the general plant conditions. That's going to help us establish the cost benefit ratio for the site. We want to look at developing the trap standards. Again, what are we going to do after the survey results come in to make long-term improvements to the system? Ideally, we even want to try to establish the database for the traps before we go out in the field. All of these things save time once we get out into the field. So once those building blocks have been put in place, we can go out, do the survey, we can analyze those survey results, and because we've already developed the trap standards, we can begin the trap replacements immediately. Then once that's done, those are put in, the replacements can be tested and updated in the database. We can review the standards to make sure we didn't miss anything or to make sure that there are no changes to be made. And then that cycle can repeat itself. And that's what will keep the program sustainable and moving forward, is by having these building blocks in place. So next, we're going to talk about, again, implementing a long-term total cost of ownership model for steam trap replacements. So how do we do that? It's important to look at minimizing the cost of the traps over a period of time. If we simply throw traps in and they fail in a short period of time, we're constantly, again, going to be chasing as opposed to resolving these issues in the long term. So we want to establish what the plant priorities are for the traps that they're going to select. Their maintenance activities, their longevity, energy efficiency, initial cost. Then we also want to evaluate the plant conditions. What applications do you have? What steam pressures are there? What specific challenges in terms of applications? What's the installed base currently, and what's the availability of resources to actually change traps? Based on that, we're going to begin looking and selecting the best trap technologies based on those sets of criteria. We're going to look at the reliability and energy efficiency of the replacements that we put in. And again, we're going to select products for those special applications that may need a different product. All of that is going to help us achieve the lowest total cost of ownership for that drain location over a longer period of time. So let's start looking at the life cycle cost of a steam trap. On the next slide, you'll see we lay out what is the true cost of the trap. Well, most people associate the cost with just the purchase price and maybe the labor price to put it in. But there are other criteria like the functional steam loss, how much steam the trap uses during normal operation. And there's a standard to guide that manufacturers can provide you with that information. The other thing that we want to look at is ultimately, as a mechanical device, that trap will fail. What does it cost when it fails? If it fails closed, what are the risks involved with that fail closed? If it fails open, does it have too large of an orifice? Is it too oversized for the application? And could it lose a lot more steam than maybe we would want? So let's look at 4 traps and how each of them are different compared to their purchase cost. We'll start evaluating these by looking at the four factors for the system. So the first is going to be the failure impact that we were just talking about. What does it cost when it fails? Or look at the functional steam loss. How much does it use during normal operation? Of course, we'll look at the installation cost, and finally the upfront cost, what the purchase price is. So over a 10-year period, we're going to compare these 4 traps. So trap A, we look at that, upfront purchase price is $350, but when we look at the life cycle cost of that trap, we see its total life cycle cost over that 10-year period is about $900. Next, 953. So trap B, slightly lower purchase price, $225, but again, that 10-year life cycle is going to average out to be about $2,200. Maybe it doesn't have as long a life. Maybe when it fails, it's losing more steam. Trap C, it's about half the cost of trap B, but as you can see, the life cycle cost of that design is going to be somewhere in slightly higher than trap B. Next. So it's about $2,500. And then the last trap, trap D, although it has the lowest purchase price at $90, you can see it has the highest life cycle cost. And this is one of the mistakes we see clients making sometimes when they're doing their replacement assessments. They're either replacing it directly in kind, or they're not getting the maximum value from those locations. If you want to reduce the number of traps you put in, you want to make sure those traps last longer, and you can do that by focusing on that total cost of ownership. So now let's talk about the trap standards and how we develop those and what goes into those. So TLV has a process called a S.T.A.R. It's a steam trap application and review. The first thing we're going to do is we're going to establish the technical specifications for a site. These are things like plant steam pressures and temperatures, plant materials of construction requirements, carbon steel, stainless steel, their connection preferences, and those are all going to go into a data sheet. We're going to use that to come up with a matrix based on the application. So again, this gets us out of the replacing kind mentality or the crossover mentality, and we start applying traps based on their application. And then those are going to, again, be based on the performance, life cycle cost, and typically we give a best solution and an alternative solution. And then lastly, as part of that application and review, we're going to establish best practices for installation. Any trap, no matter how reliable it is, if it's installed incorrectly, is likely not going to achieve the lowest cost of ownership that we would like it to. So that information, once it's done, we take that and we convert it into a usable format called a pocket application guide or a P.A.G. These typically consist of laminated cards that we hand out to anybody that's involved in the management of the steam system. That could be operators, it could be mechanics, it could be contractors. This helps ensure that whether it's a survey response or just general installation of traps on a day-to-day basis, that the traps are correctly selected, they're correctly installed, and we're maintaining that standard that we've set up. These laminated cards, basically on the front, you've got the application, the pressures and temperatures, there's a picture of the product, we give you sizes, takeout dimensions, even a storeroom number if you have an SAP or a storeroom number, so that in-house personnel can properly access that from your storeroom. And then on the back of the card, we're providing, again, that installation detail so that your people putting in the traps can recognize when the CDL location is not up to the standard, is not up to the best practice. And then as a group, you can decide how you want to address those and in which way you want to address those. This can also be done as a full poster where we can put this in maintenance areas or operational areas, as well as a storeroom to help out there. So the next thing we're going to talk about is, again, planning the survey. A lot of the emphasis that we're putting here in this presentation is doing upfront planning. Like any project, successful projects spend a lot of time planning upfront so that we don't have to make changes on the run as the project progresses. So in the planning for the survey, there's two areas of logistics that deserve special attention. Next, the first is trap access. So are there hazardous areas or confined spaces where special permits or PPE is required? Does gas monitoring have to be performed? Is there special equipment required to access traps, ladders, man lifts, things like that? Insulation is a big one. A lot of times traps are insulated over. We need the trap to be stripped of insulation so that it's accessible for testing. Also, insulating traps can sometimes impact their performance. So we want to have that discussion of whether the trap should be permanently insulated or some other safety precautions should be taken for personnel protection that don't involve insulating it. And then also discuss what means are used to identify the traps, their locations, how they're described, so that the information in the database makes sense to folks going back out to do the replacements. The next is operator support. We mentioned this earlier. It's critical to find the traps, but also really to determine what their service is. Are they really out of service? Is it something that can be put on temporarily for testing purposes? Operators typically, hopefully, are going to have the authority to open valves and do things like blow down strainers so that we can more accurately diagnose cold installations. and we don't just list them as cold and then nobody knows what their actual condition is. Next, typically, the first set of data that's collected in most surveys consists of an area, a trap ID, a model, maybe a connection and a location. But the best trap management programs go a little bit further, and we want to focus on 3 specific areas of data points that we collect to ensure, again, better analytics. One is application data, not just your basic drip tracer process, but is it a saturated steam main? Is it a superheated steam main? Is it the end of the steam main? On your tracing system, is it instrument tracing? Is it copper tracing? These may have different criteria and may be subject to different reliability. On your process, is it on a reboiler or a turbine or a flare, and how important are those particular pieces of equipment, which leads us to the next piece of data that we want to collect, and that is the priority. Is the process or is the application on a very critical process or on a safety critical process? These are important things to know, not only from a maintenance response standpoint, but also from an inspection standpoint. As we look to optimize the program and maybe change inspection frequencies over time, we may want to increase the inspection frequency on very critical applications, and maybe decrease it on general applications. So that allows us to optimize the inspection frequency. And lastly, we also want to know what the operation of that drain location is. Is it continuous? Is it modulating, seasonal, intermittent? When we go out in the field, again, when we're trying to optimize the testing phase, certainly we don't want to test seasonal traps out of season. If the trap is not in service or valved out, hopefully there's a good documentation package to explain why that is, and we want to make sure that that's included in the notes for the survey. And then the last thing we're going to look at in this section is the implementation of the Z.R.M. So the key factors for implementing that zero reset maintenance are pre-planning the maintenance response, getting the site planners and the suppliers involved, making everyone familiar with the S.T.A.R and what we're going to be doing and how we're going to be addressing non-conforming CDLs. Next, we want to talk about the pre-planning of the purchasing and the stores, making sure there's sufficient stock to begin so as we don't slow down the maintenance response time, and that we've got good communication between purchasing and your suppliers for additional inventory support. The next thing we want to look at is pre-installation training, getting your maintenance people hands-on with the products so that they understand what's going to be coming, familiarizing them with the pocket application guides and the posters so that they know what's coming. And then now, once that is all done, we can start the installation process, replace the traps, which can then be tested and validated to confirm their proper operation. And then once that's done, we can record that maintenance in some type of site action log, update our database, and then do our progress reports and our stewardship to show how the program is progressing.
Great. So we've covered a lot about planning and execution. It's also important to make sure that what is happening is actually what we hoped for. And we use a term called stewardship that does that. It has a stewardship report. We discuss that with the program manager in the plant and then jointly take action. And the primary goal of this is to see what's actually happening and compare it to the plan, because sometimes there are surprises. As we do that, we want to make sure that we can see benefits are actually being achieved and that we quantify them, and that we make the plant aware of the existing exposure to risks that they may have. We also want to identify what other benefits are remaining. And finally, we need to make sure that we're finding ways to improve that program. Now, this is very different than perhaps the traditional once-a-year survey program, where a survey gets done, a report is generated on the findings, and then hopefully the plant take action. And then 1 year later, the plant do the same thing. So we want to introduce a slightly different paradigm. And this is also more applicable to plants that want to do multiple tests a year, and to very large plants where the testing and repair work never stops year round. So we're going to still do the survey, we're still going to do the repairs, but this time we're going to update a database. Now, if we only do this once a year, that's great. A year from now, we do it again, but we'll now have a database of several years' information. And that allows us to do some really advanced analytics, which I'm going to show in a moment. Now, for the cyclical plants or the plants that test the whole year through, they may do some more testing over the course of a year. And we may need to pull information now to report on the year's progress from multiple surveys, from multiple repair periods. And we also want to know at any point in time, well, hey, exactly where are we? So let's have a look at a few things that we can pull out from a stewardship report. Now, this is going to be based on illustrative data, and I've simplified it, and I've simplified the material I'm going to present so that it's easy and quick for me to present. So let's start out high level, and we can see here's the plant. It's got 2,025 CDLs. They've inspected them 2,000 of them and done 2,000 tests. We can see how much value they found and exactly how much value the plant can still capture. And we can drill into these 2 points in a little bit more detail and see the actual survey findings. We can also see the actual current status. So in this example, we can see they found 281 leaking locations, and they've repaired some, and now they're ending up with 136. We can actually see what happened on the maintenance side. So we can see here, they repaired 159 cold traps. That mitigated risk with this value. They eliminated steam loss with that value. And we can even quantify that in pounds an hour and determine how many traps they replaced. Now, we can also look at the maintenance data by some other angles. So for example, we might look at it by month and track that repairs are actually happening and repairs are going according to plan. We could look at things by area and see if there are any difficulties in one particular area. And for steam leaks, we can look at things by pressure level. And this is showing what steam savings we made at each different pressure. And that could be important to feed into a steam balance to try and close the gap. On the inspection side, we can look at things by time. And a good one to look at is how many inspections are being done each quarter. So here we've got 2011 inspections, here we've got 2016 inspections in Q1, and then down here, bit of a surprise now, we only did 8 inspections in 2017. So the program manager might want to be a little concerned now because this is a lot lower than the historic averages. We might want to keep track of that for the next quarter. And if things haven't picked up, maybe track things monthly. Now, all this data's in inspection date is in the database. So we can actually look, when was the last time a location was inspected? So here on the far right, we can see there's 2,025 locations. 2,000 of them were tested in 2019, but 13 of them have never been tested since 2007. Now, there may be a legitimate reason for this. It could be an area of the plant that's closed down, but equally it could be that these traps have just fallen off the testing schedule. Maybe they're a little bit difficult to get to. Well, if that's the case, we need to resolve that and inspect them to make sure that these locations can't result in some form of an incident. Now, Richard also mentioned the importance of prioritizing traps. And within a certain testing period, we can actually see how many very critical locations were actually tested. And in this case, the plant probably might be a little concerned because it didn't test all of the very, very critical traps. We can see what the current status looks like. And again, we might be very concerned if we saw that there are 16 cold locations on very critical applications. Richard mentioned about doing the S.T.A.R to identify what the plant believes is going to be the best model for them. So we can actually track that and see what is the current makes and models that are in use in the plant, and specifically what models were being installed during a particular period of time. Now, so far I've covered things that keep the program running and make things visible so we can see whether the program is on track or not. We also need to improve the program year on year. And one of the fastest and easiest ways of doing that is to look at short life traps or repetitive failure locations. So here I've got a graph. On the x-axis is the number of times a location has had a failure, and on the y-axis is the number of locations having that problem. So on the far left, in my example, I've got 700 locations with absolutely no failures. Halfway along, we've got 223 locations with 3 failures. But the real interesting one is right over here on the far right-hand side, where we've got 10 locations, and each one of those had 8 failures. So there's a total of 80 failures there. And that's particularly important since there's only 8 years of data in the database. So if we can eliminate these frequent failures, it's going to help improve the program in the future. So we need to identify them. Well, that's easy. We've got the database. We can pull them out. When failure is detected in one of these locations, we need to open up the trap and see why it failed. But more importantly, we need to go out into the field and review the application. Because in our experience, the frequent failures are due to the application rather than the product. Now, this combination of information on why did the trap fail and how is the application in the field will allow us to identify a root cause, which we can then remedy, and then move on to the next most frequently failing locations. If we do that and several other things to improve the program, we'll actually be able to plot some of the graphs that Richard was showing earlier. For example, we can show year by year what our inspection results have been. So we can see from this one, wasn't much improvement in the first 2 years. There was some great improvement in the next 2 years, but then the plant took a gap year. And unfortunately, that showed itself in the subsequent year because all the failures from the year before didn't get addressed. They appear when the plant does the survey the following year. It's really important to try and avoid those gap years because on large plants, so many failures may occur in that gap year that the plant does not have enough resources to catch up. And it may take multiple years to recover the traps back to a good population status. Now, the data I'm showing here, that's got the same number of inspections in every year, and that's seldom the case. So we might need to just look at that on an annualized basis and look at percentages.
So let's review some of the ideas presented so far and discuss how to continuously improve our program year on year. So next, we're going to look at the new paradigm that we've discussed. It focuses on long-term benefits as well as upfront planning to ensure the program delivers those benefits. So our initial discussions, we want to focus on what are the targets and initiatives for that site. We want to establish our goals and outcome expectations. The next thing we want to do is our preliminary data collection, our walkthrough, our sample survey to establish that cost benefit analysis. Then in the pre-inspection phase, we want to establish the program budgets. As John mentioned, if the initial walkthrough or the sample survey shows a number that's going to far exceed the amount that the site is comfortable budgeting, it's much better to scale the program back and do a smaller program completely than simply to go out and collect data on traps that are failed and then not be able to replace all of those. We also want to develop those S.T.A.R documents, the draft of the S.T.A.R, get that reviewed and signed off by everybody. And then once all that's done, we actually want to go out and do our CDL inspections. We want to identify those defective CDLs. And then lastly, we want to follow up on the survey. We want to make sure that we conduct the Z.R.M of the traps that we inspected, that we record those installations, ideally retest those traps, and then continue stewardship reporting to check our milestone goals, to check and see where we are. So what does a complete CDL management process look like? Well, a sustainable CDL management program has to have three key things. It has to be simple, it has to be accurate, and it has to be repeatable. So that involves accurately detecting those CDL failures, identifying the root cause of failures and eliminating repeats like John was showing, correctly replacing your defects with your best solutions, and importantly, performing Z.R.M, getting all of the traps that we identify as bad repaired, and then periodic reporting of that so that, again, we can see where we are, and if we start to deviate off the path, we can do a course correction so that we can keep the program moving and deliver the benefits that we identified in the beginning. So the last slide, moving forward for continuous improvement, we want to monitor those key activities, things like inspection rate progress to make sure that we're not having any gaps, repair activity rates to make sure that traps that we identify are bad are getting repaired, recommissioning not in service traps where applicable, or eliminating abandoned in place traps from the database. Next, we want to look and confirm that the replacements are matching the S.T.A.R, whether that's a survey result or just a trap that goes bad in between being surveyed. We want to make sure that everybody is on board with the S.T.A.R program. We want to target high returns and high risk areas and make sure we're focusing on not only just leaks, but also cold traps. And we want to take those repetitive defect areas and do root cause analysis. So we want those traps back so we can evaluate them. And lastly, we want to review and improve that program. Each time we do stewardship reports, we want to look at the lessons we learned from the previous activities. We want to use the data that we're collecting to validate the program and validate the ideas that we have so we can move forward with those. We want to track our historical progress, and we want to identify additional program savings. Programs are going to be more sustainable if we can optimize just the program cost as well as optimize the asset itself. So that brings us to the end of our presentation. I'm going to ask all my co-presenter and all our support people to share their webcams again. So unfortunately, we went a little bit over. I apologize for that. So we're not really going to have a chance to do a Q&A here at the end. Hopefully, if you did submit a question, our team got back to you. If they didn't, we will be responding to those throughout the course of the rest of the day. If you do have any additional questions after the presentation ends and you would like to send those to questions@tlvengineering.com, we'll certainly follow up with you if you have some specific site-related questions, or you want to see what this program might look like with a sample survey, something like that. Please reach out to us and we'll put you in touch with the correct TLV resources to do that. So thank you very much. Appreciate it. Glad to have you here, and we'll see you again in the near future.